The whole reason we're learning about limits is so that we can use them to define what's called the derivative in calculus. So this is all building up to that. The way in which we define the derivative, if I were to draw a picture here, get rid of this guy. The difference quotient says that, and then I'll draw the picture. The difference quotient is, it's a quotient. You see that it's a quotient? Okay, and the difference part is right here. Okay, the difference part is the minus sign. And what the difference quotient is it's really just a hidden version of your slope formula from Algebra 1. Right? It's a hidden formula, or a hidden version of your slope formula from Algebra 1. It says f of x plus h minus f of x over h. And let me demonstrate to you what I'm talking about here. From Algebra 1, we had this slope formula that was y2 minus y1 over x2 minus x1. You remember that? Here's what the difference quotient is doing for us. We have, for example, a curve. And in calculus, we want to find the slope of a tangent line to a curve. But here's the problem. A tangent line to the curve only touches the curve at one point. So pretend it's touching the curve right at that dot. We need 2 points according to our slope formula from Algebra 1 to find the slope. So what we do is we combine the idea of the slope formula from Algebra 1 and the idea of a limit to come up with the definition of the derivative, which is the slope of the tangent line to a curve at a point. And so the way it works is this. If I have, let me go ahead and so what we're going to do is we're going to say, okay, if this is the point x right here, say this is x, what we're going to do to create another point is choose a point arbitrarily close to x. Does that sound kind of familiar? As close as I possibly can. And we're going to call that point on the curve. Now that's not really very close, but pretend it's as close as you could possibly be. So here is this point, and this point is at x plus h. And so what happens here is that there is some function represented by this curve, and by plugging in x plus h to that function, I get y2. Right? So f of x plus h is my y2 in the slope formula from Algebra 1. And f of x is my y1. Okay, it's this other dot here. We'll put that in blue. So here's my dot in blue. That's y1. The dot in red is my y2. And then you'll notice that in the difference quotient there's only a single variable h representing these two values, x2 minus x1. Well, what we do in calculus is we say, okay, let's consider the limit as h approaches 0 of this difference quotient. We're going to consider the limit as h approaches 0. So what we're saying is that as the difference between x2 and x1, as these 2 points come closer together, then we get closer and closer to the slope of the tangent line to the curve. It's like taking this red dot and just sliding it towards the blue dot until it finally matches. That's the idea behind the limit there. So it's the limit as x2 minus x1, as these two get closer together, approaches 0. And so that's why there's only one single value right here. Okay? We call that h. So the difference quotient is really just your slope formula, y2 minus y1 over x2 minus x1. And when you apply the limit as this difference, x2 minus x1, gets as small as possible, then you have what's called the derivative, or slope of the tangent line to a curve. So that's the idea there. It's the idea that you've probably looked at this before. If you take on your calculator and you do a curve on your calculator, we can even do it now. Let's do a particular curve here. I'll show you. And graph sine of x here. And then what I'm going to do is zoom in on this curve y equals sine x close to the origin. So there's definitely a curve, right? But what happens if you go to zoom and you choose Z box? It's an option, that's number 1. So this thing doesn't freeze on me. And what you do is you this thing over a little bit. Okay, I'm going to mark right there. move up a little bit. And over a little bit, it's creating a little zoom box right there. And mark it there. It's zooming in, actually a little bit above there. What does that look like as I zoom in there? It's starting to look more and more like
a line.
It is. It's starting to look more and more linear. As a matter of fact, let's see if I can zoom in one more time here. It's still in there. I might have zoomed in the wrong spot. Oh, there it is. Now you can really see it. So it looks just like a line over here. And so the idea is that as you zoom in on a curve, closer and closer and closer, any curve looks linear. You zoom in on that. So it's called local linearity. That's a big idea behind calculus. All right. So we have this difference quotient, and we're going to use the difference quotient to find the value of the slope of the tangent line. So as we're going through these when it says find the limit and you see this difference quotient type of thing, what I'm asking you to do is actually find the slope of the tangent line to the curve x squared at x equals 3. Oh, that's weird. So at a particular point. So I'm not sure why it says f of x equals 3 right there. All right. So we have the function f of x equals 3x squared, and we are going to find the limit at -2. You see the -2 right here and right here? So that's the point at which we're finding the slope of the tangent line to the curve. So here's how this works. It says f of x plus h, this is a good review, means plug in x plus h wherever there is an x in this function. Okay? So when I rewrite this, it looks like this. We got to copy down the limit. We cannot drop the limit until we plug in 0 for h. And we can't plug in 0 for h until we can cancel h with something on top. Because at this point, if I plug in 0 for h, I'm going to have a problem, right? So somehow there must be some simplification that will happen here that will allow me to cancel out the h and then go back and plug in 0 for h, like we just did in the calculated limit section. Okay? So lots of algebra. Here we go. It's so the limit as h approaches 0 of the function is 3x squared. So we have 3 times something squared minus 3 times something else squared over h. So I'm going to take the -2 plus h here and plug it in every time I see an x. So we have -2 plus h, we're going to plug that in for the x. And then here, this is saying plug in -2 for x. So what you see in blue and green here, I'm plugging in for x in this function, okay? Not the other way around. This is f of x notation. So we're plugging in -2 plus h, or -2 for x. All right, then a bunch of algebra takes place here. So you ready? Hopefully I gave you enough room on there. Limit as h approaches 0. What's -2 plus h squared? Can you expand that out? What's the first term going to be? Middle term, last term? 3 times, first term will be 4. And then the next term, so 4, and then -2 times h is -2h. Double that, we have -4h. And then plus h squared. And then we have -3 times, now we're going to plug in -2 for x in this function 3x squared. And so -2 squared is 4. And then all over h. All right. So we have the limit as h approaches 0. As I distribute here, you'll notice that things will start to cancel out. And if that doesn't happen, you've done something wrong in your plugins, okay? So 3 times 4 is 12. 3 times -4h is -12h plus 3h squared minus 12 all over h. And notice what happens to the 12s. See you later, they're gone. And so I have limit as h approaches 0 of negative 12h plus 3h squared over h. But what's common to each of the two terms left over here? H. So I can factor out an h. I have negative 12 plus 3h over h. And then if I cancel my h's, can I now evaluate the limit? If I plug in 0 here, 3 times 0 is 0. That leaves me with negative 12, right? So what this is saying is that if I look at the function y equals 3x squared, what does the function y equals 3x squared look like? Well, it's a parabola facing upward. It's fairly steep, right? Goes through the origin. Here's what I'm saying. If I go over to x equals negative 2, and if I draw the tangent line, do a red dot here, at x equals negative 2, the slope of that tangent line at x equals negative 2 is going to be negative 12. That's what we just found. So we found the slope of the tangent line to that particular curve, y equals, or f of x equals 3x squared at negative 2. And that is called the derivative, which will be introduced to you next. Are there easier ways to find the derivative than going through this algebra? And the answer is, what do you think? And you'll spend much time next semester learning those techniques, okay? So you'll appreciate that. Your calculus teacher will be the hero. I will be the villain. All right, so we have another function here. F of x equals x cubed is the next one. And we're going to find the limit of this function at x equals what point? What point am I asking for you to find the limit or the slope at? At 2 this time instead of negative 2. Do you see the positive 2 in there in place of x? So it'll look like this. Limit as h approaches 0. Now I have a new function, right? I have a new function. And my new function is x cubed. So I'm going to take this 2 plus h, and I'm going to do what with it? I'm going to put it in here for x. And so it's going to be cubed. And then minus, I'm going to take the 2 here and do the same thing with it. Plug it in for x. And so that's cubed as well, all over h. All right. Remember how to expand 2 plus h cubed? This could be on your final. This is something that could be. Remember we talked about 1 minus h to the 4th? Same idea? How do we expand 2 plus h cubed? Use Pascal's triangle would be one way to do it, yeah. So we have the limit as h approaches 0 to whatever we get when we expand out 2 plus h cubed. So let's go ahead and expand that out. Okay, so when we expand that out, we have 1 times 2 to the 3rd, which is, we'll write it out here, is going to be 8. And then plus 3 times 4 is 12. H to the 1st. And then plus 3 times 2 to the 1st, h to the 2nd will be 6. Oops. Plus 6h to the 2nd, plus h to the 3rd. And then don't forget we have this other term over here. Minus 2 cubed is going to be 8. And then over h. Do you see why we need that 8 in here? Yeah, that's what gets rid of the other 8. And this is what will happen each time. If you know what already is going to happen, then you'll know if you've made a mistake algebraically. The constant should cancel out. For the purpose of factoring out the h, so I have a new limit here. Limit as h approaches 0 of, see this h that's common to each? If I factor that out, I'm left with 12 plus 6h plus h squared all over h. The h's cancel. Now can I plug in 0 and get a different result than I would have otherwise? I think so. This becomes 0, that becomes 0, I'm left with just 12. And so the difference quotient, or what you're later going to find out, the slope of the tangent line is 12. All right. So I defined a tangent line here. I already introduced you to that, but there's the definition if you want to write that down. Tangent line is to determine the slope of a curve at some point on the curve. At a single point, you find the slope of the tangent line at that point. And we find the slope of the tangent line by using the difference quotient and then evaluating its limit as h approaches 0. So the difference quotient was just this up here, right here. This is our difference quotient. When we apply the limit to the difference quotient, like we did in these two examples here and here, then we're finding the slope of the tangent line, or what will later become known as the derivative. Okay? So here's our picture right here. We've got this red line. If you want to find the slope of that red line at negative 2 comma 4. So it says, use the graph to approximate the slope of f of x equals x squared at negative 2 comma 4. Just using the red line that I've drawn, what points does the red line go through if you're going to approximate the slope? We know it goes through negative 2, 4, right? And it also looks like it goes through negative 1, 0 down here. So this would be an approximation, not the exact value of the slope of the tangent line like we could find with the difference quotient. But an approximation would be m equals, this is going back to algebra 1, y2 minus y1, so 4 minus 0 over negative 2 minus negative 1. And so I end up with an approximation of 4 over negative 1 or negative 4. Does that look like a pretty good approximation to the slope of that particular tangent line for y equals x squared? It's about negative 4. Not a bad approximation. All right. The slope and the limit process, I talked a little bit about that already. The best we can do to find the slope between, or the slope of the tangent line, is to actually find the slope of what's called the secant line first. If you go back up to my picture up here, that's what I was doing with this x and x plus h. I'm using a secant line, which goes through the blue and the red point, as an estimate of the slope of the tangent line, which is in black right now. Okay? So when we apply the limit to the slope of the secant line, then we get the slope of the tangent line. And that's where that difference quotient comes from. As we make h smaller and smaller and smaller, we're sliding those points together. The secant line becomes nearly the tangent line. Okay? As we slide those closer and closer together, the secant line becomes nearly the tangent line. And that we call the derivative. So the slope of the graph of the tangent line to a curve at a point is the derivative. There it is. So the slope of a curve at a point, at the point x f of x, is the limit as h approaches 0 of f of x plus h minus f of x over h. So you take the difference quotient, which is really our slope formula from back in algebra 1, which finds the slope between 2 points. When we apply the limit as h approaches 0, or as this down here, the difference between the x2 and x1 gets really small, then we have the slope of the tangent line, or the derivative. Any questions on that? All right. Let's do a couple more calculations here. We're gonna save the power rule for next year. So I think I might have taken that off the ordinance. Yeah.
For slope, finding of a graph, are we always just going to be using the m equals y2 minus y1? Or will we,
For finding the slope between 2 points,
Yeah,
which is
just-
the slope of the
just
secant
that.
line, you're going to use that, y2 minus y1 over x2 minus x1. If I ask you to find the slope of the tangent line to the curve, or the derivative at this point, you're going to use this expression right here, which is the difference quotient with the limit applied to it. Okay?
But isn't the one we found the tangent line?
For this problem, yes, but to try and find the slope of the tangent line to a curve using this formula, we won't be perfectly accurate. The slope of the secant line, look at this right here. See my green one and my black one? They're different slopes. And so the secant line becomes a better and better estimate the closer the red dot gets to the blue dot. But you have to apply this entire formula to get the exact slope of the tangent line to a single point. If you don't use the limit in here, as h approaches 0 of this, then you don't get the exact value of the slope of the tangent line. If you leave this off, then you'd have to have two values down here, x2 minus x1. And then you would get the slope of the secant line, which is not quite exactly the same as the slope of the tangent line.
Okay.
It's very close. And it gets closer as you slide those points together. That's the conceptual idea. All right. So it says find the formula for slope. In other words, find the equation of the slope of the tangent line. Okay, these are all asking the same thing. So use that to find the slopes at two other points. So what I'm asking you to do right here is to use that difference quotient to find the slope of the tangent line. So let me write down the difference quotient. We have limit as h approaches 0 of f of x plus h minus f of x over h. Now notice, I am not putting in a specific point here. I'm going to find a generic equation or formula for the slope. It will have x's in it, it won't come out to be a specific number like on the previous two examples. Okay? You won't just get one number. You're going to get a formula, and that formula, if you plug in 0 or -1 to that formula, it will give you the slope of the tangent line, well, an approximation for the slope of the tangent line at those 2 points. Okay? So, actually, it will give you, I take that back. We will get a formula that when you plug in the x coordinates of either of these points will give you the exact slope of the tangent line at those points. Okay? So, this one's tricky algebra. Okay? F of x plus h. So I'm going to plug in x plus h everywhere I see an x in this function right here. So this is going to create a messy complex fraction. We always love this in algebra or in calculus. This is a fun one. The next two are fun ones here. So limit as h approaches 0 of 1 over, in place of x plus 2, I'm going to put x plus h plus 2, and then minus 1 over x plus 2. So here's what I'm doing, all over h. I am plugging in x plus h for x in this function. So a lot of students want to just go the other direction sometimes and plug this in here, but we're plugging x plus h in right here for x. So I have 1 over x plus h plus 2. I always get the question, where's the plus 2 coming from? The plus 2 is in the formula. I am only replacing the x with the x plus h. And so it does make for some messy algebra here. Okay. We have a complex fraction. And what do I have to do with this complex fraction before I can cancel anything? Remember? We'll come over here. We're going to need a lot of room. So it's the limit as h approaches 0. I've got to get common denominators here, right? Ooh, yeah. If you're groaning, you understand what I have to do. Do these have anything in common? Well, they have some things in common, yes, but are they, in other words, does this divide into this at all? No. Does this divide into this? No. Well, we will have to get rid of the h, that's the goal. But before I can subtract these two and get it into one fraction, I have to multiply this fraction by this whole thing, and I have to multiply this fraction by this whole thing. I hear some groans. You're understanding that. You have a correct understanding of the algebra that needs to be done now. So I have 1 over x plus h plus 2 times x plus 2 over x plus 2, and then minus 1 over x plus 2, and what do I have to multiply that by? Yes, x plus h plus 2 over x plus h plus 2. And that's all over h. So now some magic will happen. Don't worry. Don't panic yet. So we have the limit as h approaches 0. As I distribute here, I have x plus 2. But then when I distribute that minus sign, do you see what happens? X plus 2 minus. Groans should be turning into shouts of joy here. I'm not hearing the right response here. Minus x minus h minus 2. All over x plus h plus 2. Don't worry, we're not going to expand this out. X plus 2 over, I'm going to write this as h over 1. Okay? Look what's happened here. X's are gone, right? 2's are gone. It's looking better all the time. And so this becomes the limit as h approaches 0 of negative h over x plus h plus 2 times x plus 2 times what fraction? 1 over h. That's right, 1 over h. And so the h's now can cancel. We figured out a way to cancel that h on the bottom. If you haven't canceled the h on the bottom in these difference quotients, you've done something wrong in your algebra. The h is canceled, so now I have the limit as h approaches 0 of negative 1 over x plus h plus 2 times x plus 2. And what happens then when I plug in 0 for h? Plug in 0 for h, that's gone, so I have negative 1 over what? That's 0, I have x plus 2 here, and another x plus 2 here, which we call that x plus 2 squared. So that's my formula. I'll box it right here. That's my formula for finding the slope of the tangent line to the curve 1 over x plus 2 at any point. You give me any x coordinate, I can tell you the slope of the tangent line. Okay? Let me draw a picture here for you. So if I went 1, 2 over, I'd have a vertical asymptote. I'd have a branch right here. I'd have another branch over here. Okay, there's the parent graph, or there's the shifted parent graph for 1 over x plus 2. Here's what I'm telling you. This formula right here will tell you the slope of the tangent line at any point on this curve. Okay? Any point on this curve, it will tell you the slope of the tangent line. So when I ask you to find the slope at 0, 1/2 and negative 1, 1, all I'm doing is plugging in the x coordinates of these. So if I want to find the slope m at 0, 1/2, what I'm going to do is find negative 1 over 0 plus 2 squared. And so negative 1 over 0 plus 2 squared gives me negative 1/4, right? 0 plus 2 is 2. 2 squared is 4, so it's negative 1/4. So the slope at 0, 1/2 is negative 1/4. What would the slope be at negative 1, 1? Would be m equals negative 1 over negative 1 plus 2 squared. And what does that equal? Negative 1 plus 2 is 1. 1 squared is 1. Negative 1 over 1 is negative 1. Look at right here in my picture. If I went to x equals negative 1 and I put a dot here and I drew the tangent line, does that green line look like a slope maybe of negative 1? Look like that green line would have a slope of negative 1 maybe? Okay. And then at 0, we'll do a different color here. Put a blue dot here at 0. Could that be at 0? I didn't draw it very accurately, but could that blue line maybe have a slope of negative 1/4? Definitely negative. Looks a little steeper than 1/4 the way I drew it. But if I drawn it accurately, at x equals 0, y equals 1/2, I would have had a slope of the tangent line of negative 1/4. So the difference quotient, when you apply the limit to it, is the slope of the tangent line to a curve, which we will find out is the derivative. Okay. I think I'll go ahead and I have one more to do, and then I'm going to stop. It says find the formula for slope. So I give you one more on here. P of x equals square root of x minus 4. This is always a fun one, too. This uses the conjugate rule that I showed. Okay. So we have the formula for the slope will be what we get when we evaluate limit as h approaches 0 of, once again, f of x plus h minus f of x over h. And so I have limit as h approaches 0. Let's go ahead and plug in x plus h here. So I have square root. In place of x, I'm going to put x plus h, and then minus 4. And then what you may have noticed is that when I plug in x to the function, it doesn't change anything, right? All I'm really doing is substituting in the function with x in it for f of x. That's all that I'm doing. All over h. And so how am I going to get rid of those radicals? Understand what we're doing algebraically. I should hear some groans. Really? What's the conjugate to this guy? It's a long one. You know what the conjugate to the top of this is? Yeah, there you go. You get it. It's square root, but magic will happen. Don't panic. Oops, minus 4. And then we'll wrap it up with this. I won't torture you anymore here. So minus 4 minus square root of x minus 4. We're going to take and put that in parentheses over h, and we're going to multiply that by its conjugate, which is square root of x plus h minus 4 plus square root of x minus 4 over square root of x plus h minus 4, and that's all under the radical, plus square root of x minus 4. So the conjugate is just this same thing with a plus sign in between. What a mess, huh? All right. So limit as h approaches 0. When I multiply this by the conjugate, what's going to happen to the radicals? They disappear. What happens to the middle term? What happens to the middle term of the trinomial? This is a trinomial in radicals. That's something else, huh? But what happens to the middle term of this trinomial? This is going to be positive. This will be exactly the same thing in negative. Cancel out, it'll be 0. Over here going, oh, what a headache. So we have x plus h minus 4 minus x minus 4 all over h. All the radicals cancel out. All the radicals on top cancel out. I still have the radicals on bottom. But watch what happens here. If I distribute this minus sign, what happens to the x's and the 4's? They cancel out. And you need to have these parentheses here. Okay? It's minus the quantity x minus 4. So the x's cancel out. The 4's will cancel out. And I'm left with just an h on top. And what happens to the h? What happens to the h here? The h cancels out as well, but what different type of canceling, right? This is a canceling to equal 0. The h is a canceling to equal 1. Yeah, the different types of canceling. So the h's cancel out after you cancel these out. And you have limit as h approaches 0 of positive 1 over square root of x plus h minus 4 plus square root of x minus 4. And when you plug in 0 to that, what do we get? There's 1 over, plug in 0 here. Plug in 0 here, you have square root of x minus 4 plus square root of x minus 4, which is 2 square roots of x minus 4. So what would be the slope if I plugged in 5? If I plug in x equals 5 here. Or if I plug in x equals 8 here. So if I plug in 5, it's 5 minus 4 is 1, square root of 1 is 1, 2 times 1 is 2. So the slope at 5, 1 is m equals 1/2. And the slope at 8, 2 is n equals, if I plug in 8 here, 8 minus 4 is 4, square root of 4 is 2, 2 times 2 is 4, so that's 1/4. So what we found, right here, I'll box it, is an equation that will tell me the slope of the tangent line to the curve p of x equals square root of x minus 4 at any point you ask me to find slope x, as long as it's in the domain. Okay, that's it. So we'll stop right there. That'll be it. I have a short homework assignment here. I'll tell you which ones I want you to do.
Do we want to explain